No, if you want it close up, then you can.
That's all.
Maybe not. That's okay. Yeah, that's okay. Yeah, you can get started. I'm not sure.
Okay, welcome back everyone.
Yeah, the presenters for tomorrow, they might show up tomorrow, right?
Yeah, that's very cool. Hopefully everyone enjoyed lunch. So in the post-lunch session, we'll have two presentations and then we get a coffee break. So we'll start with Ertugrul, who's going to talk to us about privacy and NDNs.
Thank you. In this presentation, I will talk about my PhD project. It's a part of my PhD project. It's an ongoing project. It's about the next generation networks, one of the next generation network paradigm called linked data network. So in this project, we are investigating privacy, content privacy issues in this project, and basically based on side channel timing attacks. This is the outline of the presentation, and I will give a quick shot for linked data network architecture and what is side channel timing attack. Solutions that has been proposed by others, and additionally, which this project based on an identification method in order to identify adversaries. So introduction. As we all know, the internet has been changed for content caching and increasing number of devices and number of social networks such as YouTubing, Facebooking, Twittering. But this kind of behaviors is not as suitable for IP network, because in 1974 the IP network hasn't been created for this kind of such activities, even at the moment. I believe that some of you guys consuming and producing data at the same time, but this is not a suitable method for IP networks. So the NDN has been proposed for in order to overcome this problem. One of the NDN feature is the content caching. So basically, each of named data network component, basically node, has to cache the contents in order to increase the data distribution much more efficient and much more reliable. However, caching all contents brings another problem, which is an adversary may influence the cache privacy in order to identify what has been cached, what hasn't been cached by the other connected users. So these are the motivation of my research. These techniques has been proposed by other researchers. So basically, these techniques is proposed for NDN, of course. But none of them are, it doesn't stay as efficient techniques. For example, one research has been proposed that let's divide the contents by private and non-private. But if I request a data packet that I put it as a flag as a private, it could be standard for non-private to other consumer. So it's not a very suitable technique for this kind of flag. And the other thing is encryption. Encryption, I don't, when we play with the encryption techniques, we just making the contents for just available for ourselves. But the content has to be available for all of the consumers. So when we put encryption top of it, it doesn't available for anyone. The solutions mechanism. The solution mechanism, I think they work very fine. they are suitable methods in order to mitigate timing attacks, but there is a penalty as well. So in this world, we just put our effort in order to identify the adversary first, then do solution actions for that adversary node. So the name data network, I will go for the basic stuff here. I mean, basically we have two basic packets. Interest packet has been produced by each consumer. It just carries a name. By the way, each data packet and interest packets are humanly readable. That makes it different from the IP. So we have two basic packets. Everything is humanly readable. So the data packet has been produced by producer, content producer, and each data packet and NDN has been digitally signed in order to increase the integrity. So the forwarding model, it's different than IP, of course. We have a content store first. If I'm interested with the name that I'm looking for as a data, the router goes look up first in content store. Content store is where the contents has been cached, where the contents has been cached for a certain time of period. If it's in the cache, the content store right away replies as a data packet. If it's not, it goes to PIT, pending interest and table, and here it's just the PIT dividing the interest packets for legitimate and not legitimate ones in order to mitigate DDoS attack. Then, if it's not in the PIT, the PIT send it to the forwarding interspace, and forwarding interspace look after the data packet. And the interest packet and the interest packet does not carry where the location of the data packet. It just cares how I can get it in the short way. It doesn't interested with where is it located. So whenever the data comes back from that stream, and it just the PIT make sure it's a content that is asked for as an interest packet. If it's okay, then it just cache in and send it to the consumer as a data packet. If it's not, the PIT discarding the data packet right away. So the side channel timing attack, this attack based on the privacy. Basically, it's not a sophisticated attack type, and comparing with the other side channel timing attacks. Basically, the adversary using a legitimate interest packet in order to identify the cache content in cache store. So if you sing it in the cache, the round-trip time will be much more smaller than the non-cached ones. So adversary is defining that, okay, somebody has been requested those contents recently. So the solutions are based on three methods. We can simply say to the NDN router, you can not be cached, turn off the cache. But this is so against to the NDN feature. So it's not a good idea to giving up directly from the cache, because it's one of the basic reasons that we working on NDN. The artificial delay, we can add additional delay for content store replies in order to make the adversary confused for non-cached and cached RTTs. The random caching, it's simply we can set a probabilistic number to the content store, to the router, to any node, and through that probabilistic function, router can cache the contents randomly. So implementation, we have used a name data network simulation in here. It's a C++ network simulation, and we extract the topology from an ISP topology. We have one producer screening topology in here. We have real data delays and real distance. It's a real topology. Basically, we configure the adversary. We have two adversaries here, and we have a special configuration for those two guys. Basically, we just telling the bad guys, okay, look up those famous contents. So those famous contents has been requested by the neighbor one. So in any time. So whenever they cache from those, these are backbone routers, and these are the gateway routers. So those guys having a cache content store. So whenever this guy get a data packet, this guy caching, and this guy asking for a cached one, and deciding someone has been requested for that data packet. So in order to overcome the solution mechanisms, we have used a third-party application, which is NDN based as well. It's a name data network forwarding data. So through NFT, we are able to collect special trace files from each node, and NFT can be managed for these tracer files. So the first identification method that we propose in this paper, it's a cache hit ratio. So cache hit ratio is whenever the adversary hits the cache during the attack time, it ups to the 100%. Is it clear? It is clear. But none of those nodes having that much 100% cache hit ratio. So only the adversary is having a cache hit ratio up to the 100%. So we say that if we able to identify the that guy, the adversaries, to just looking for cache hit and define the cache hit threshold values somehow in the beginning of the simulation, we can set the NFT for randomly caching, just relying on the first identification method. The second identification method is the looking after for the RTTs. So those values has been looked after from the NFT as well. So as we clearly see that the leaf 6 and leaf 13 has a very big variation than the first RTT threshold value. So we can set the NFT for just for the certain router, and whoever connect to that. Not here, not here, not here. Just for the first facing lambda, to do randomly caching in order to overcome this problem. So my work contribution is it's a challenging subject to identify an adversary in such a side channel timing network, because it's easy to deploy, it's easy to manage by adversary. It's not a complicated method, but it's a challenging topic to identify an adversary for because each type of network topology are different, and each one has a different characteristic. But in this very specific example, in that screening topology, we are able to identify an adversary. So future work and conclusion, NDN still struggles with 4 challenging privacy issues: name, content, cache, and signature, therefore the certificates. So we are trying to, we are still in process to implement our model for certificate models. Because in each certificate, we have public keys are publicly available, and anyone can ask for it, and in NDN, each certificate considered as a data packet. So everyone can ask for it. And we are working on this project for the next future work. And also, I think these two identification methods are not enough in order to identify the adversary. We need another model, such as energy consumption rates or other proposed identification methods. And the challenging one is the identifying the adversary. That's all. And for